are catching a fire. Showed you I loved you, you called me a liar. Oh no, 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 no. Baby, tell me where you gone. I've been feeling for your love so long. We can praise God in the moonlight. Baby, if you with me, better do right. And I've been gone too long, and I'm hoping that you sing my song. I've been on this road for way too long. I've been hoping that we all get along. These roads of flames are catching a fire. Showed you I loved you, you called me a liar. Give God the thanks and praises. I've been on my own, but we ain't never left alone. And if I'm telling you the feeling.
Move on to talking about indicator electrodes. There's one other thing I wanted to address, because this affects any type of indicator electrode or any type of electrochemical measurement we do. And this is the idea of a junction potential. These are potentials that exist at junctions or at where two different solutions join together that have different properties or different concentrations. And so there are, of course, errors involved with measuring anything, and this is one of the main sources of error in an electrochemical measurement. And so this is, I would say probably most common source of error in potentiometry. Because by nature you have to have these junctions for the electrodes to function properly. Okay, and so this is most commonly observed at the edges of salt bridges. And what's going on here is, that's not spelled right, salt bridges, there we go. What's going on here is that if we have a salt solution, all right, so let's imagine we have a salt bridge where we have a high concentration of sodium chloride. We have a bunch of sodium and chloride ions in connection with a water, right? Just regular water here. All right, so we have this. So this is something similar to what we have in a salt bridge, right? We have a high concentration of electrolyte because we need that to be able to diffuse into our solution to keep charge balance. Right, so salt bridges are a necessary part of connecting a circuit in the galvanic cell. So that's why this source of error is present always. Now there's going to be a small potential here, a voltage that will develop because of an imbalance of positive and negative charges. And let's look at why that happens. So where we have this barrier, right, at the edge of the salt bridge, we go from high concentration to low concentration of our ions. Our sodium and our chloride are going to want to diffuse. They're going to go from the area of high concentration to low concentration. That's just naturally what happens with anything like this. But they don't do that at the same rate. So they have different mobilities in water. And there is a table in your textbook that actually lists this. Different mobilities in water. In practice, what this means is that one of these ions is going to get further than the other. And so chloride actually has a higher mobility. So higher, spelling is just not on point today. Higher mobility than sodium. And so what that means, practically speaking, is that when this diffusion happens, right, if our barrier is here, we'll have a region towards the outside where we have a little bit of excess chloride because it got further, and we have an area here with excess sodium ions just because they didn't get as far. Right, and so I've kind of drawn these with like hard and fast lines. It's not that, here's the sodium, here's the chloride. The important point is there's a slight positive charge here and a slight negative charge here. Now, if we have a separation of charges like this, this is a potential, right? And so there's a potential that develops here. Right, anywhere you have a separation of positive and negative charges, there is a potential here. So, this is not gigantic, but is something that that is measurable, right? So this is on the order of millivolts. And so on sort of that millivolt level, you can't really get much more accurate than that in terms of measuring potentials. And this is a limiting factor in terms of how accurate you can get with potentiometric measurements. So what you ideally want to do to minimize these junction potentials is to match the mobilities. You want something that has similar mobilities for both the positive and negative ions. And that's one reason that KCl is often chosen, because potassium and chloride have similar mobilities. They're not exactly the same. There's still a junction potential, but it's smaller than you might get from other pairs of ions. So, in fact, let me just pull up that table. I have it open over here in PowerPoint. So we can see here, this table here, 15-1, we see H plus has a gigantic mobility in water compared to everything else. And if we look at K plus, it's about 7.6 times 10 to the minus 8. Cl minus is 7.91 times 10 to the minus 8. So chloride's down here. So that's why these are chosen, because they match up pretty well. And we can get an idea over here, right? Just something I mentioned here. The observed potential that you're going to measure is whatever the potential of the cell is, plus whatever this junction potential is. And for every junction that's present, right? Because you have more than one. There's not just one salt bridge. There's two ends of a salt bridge, right? So you get a junction potential from either of these. And so this gives, right, so we have something on the order of millivolts, but it can be pretty high, something like 27 millivolts if we have this junction between HCl and KCl. Whereas for, if we have with 0.1 molar KCl, but if we use a saturated solution of KCl, we get something much smaller, tenths of a millivolt instead. So this can be something really important to consider whenever we're doing any type of electrochemical measurement, specifically potentiometry, because this affects the potential that we measure.
Myself Satnam Sen. In this session, we will discuss liquid junction potential. When two salt solutions of different concentration are placed in contact with one another, ions from the concentrated solution will tend to diffuse into dilute one. The rate of diffusion of each ion is approximately proportional to the speed of ion in electric field. Suppose positive ions move with a greater speed than negative ions. Positive ions from the concentrated solution will diffuse ahead of negative ions in the dilute solution. Thus, dilute solution becomes positively charged with respect to concentrated solution. Suppose negative ions move faster, then negative ions will diffuse rapidly in dilute solution than the positive ions, and the dilute solution gets negatively charged. In both cases, an electrical double layer is set up at the junction of the two solutions.
ലിക്വിഡ് ജംഗ്ഷൻ പൊട്ടൻഷ്യൽ എന്താണെന്ന് നോക്കാം. ഒരു കോൺസെൻട്രേഷൻ സെല്ലിൻ്റെ കാര്യമാണ് നമ്മളിവിടെ പറയുന്നത്. അപ്പോൾ ആ കോൺസെൻട്രേഷൻ സെല്ലിൽ രണ്ട് ഇലക്ട്രോലൈറ്റിൻ്റെയും, അതായത് രണ്ട് ഹാഫ് സെല്ലിലുള്ള ഇലക്ട്രോലൈറ്റിൻ്റെയും കോൺസെൻട്രേഷൻ അല്ലെങ്കിൽ ആക്ടിവിറ്റി ഡിഫറെൻ്റ് ആണെന്ന് വിചാരിക്കാം. അത് തമ്മിൽ ഒരുമിച്ച് നിൽക്കുന്ന സമയത്ത്, കോണ്ടാക്റ്റ് വരുന്ന സമയത്ത് അവിടെ ഒരു പൊട്ടൻഷ്യൽ ഡിഫറൻസ് ഉണ്ടാവും. അതിനാണ് നമ്മൾ ലിക്വിഡ് ജംഗ്ഷൻ പൊട്ടൻഷ്യൽ എന്ന് പറയുക.
This video is an introduction to electrochemistry. So what's electrochemistry? Well, you might have guessed it has something to do with electricity and chemistry. And that's exactly right. Specifically, electrochemistry is about the relationship between chemical reactions and electricity. When we're studying electrochemistry, there are basically two main ways that chemical reactions and electricity interact. Here's the first one. Certain chemical reactions can create electricity. Okay, so like that's what's going on in a battery. There are chemicals inside the battery, they react together making a chemical reaction, and that chemical reaction creates electricity. Okay, so that's the first way that these two things interact with each other. The second is that electricity can make certain chemical reactions happen that wouldn't happen otherwise. We'll look at examples of both of these situations. So if we're going to be talking about chemical reactions and electricity here, let's just take a minute to explain what these two things are so we can know what we're dealing with. First off, electricity. What is it? Well, in really simple terms, electricity is just movement of electrons. I got a bunch of electrons in this diagram. They're moving in this direction, so I have electricity. Often when we talk about electricity, we're talking about movement of electrons through something. So maybe it's through a wire, or through a light bulb, or through a battery, or something like that. But if you've got electrons moving, you've got electricity. So if electricity is about moving electrons, that means the chemical reactions that we're going to be talking about are also going to involve movement of electrons. And that means that these chemical reactions that we're going to be discussing will tend to be oxidation-reduction reactions, because these are chemical reactions where electrons move between atoms. Okay, so here's how these two scenarios come into play. We can use electrons moving between atoms in an oxidation-reduction reaction to make electricity. The electrons are moving, so there's our electricity. And then for this situation, we can use electricity to force electrons to move between atoms to make oxidation-reduction reactions happen. Let's look at how that would work. So here I've got an oxidation-reduction reaction where electrons are moving from A to B. How can I use this to create electricity like along a wire? Well, what we could do is we could separate A and B, right? We know that electrons want to move from A to B, so if we separate them with a wire, then that means that the electrons moving between these atoms will have to travel through the wire, be moving through that wire, and bam, we've got electricity. Okay, now let's look at this example, okay? Let's imagine we have another oxidation-reduction reaction, electrons transferring from C to D. But imagine this doesn't normally happen because C doesn't want to give up electrons and D doesn't want to gain them, okay? Here's where we can use electricity, okay? We can take the electrical energy from a battery and use that to pull the electron from C here and to push them to D. Okay, so even if this reaction, the movement of electrons, doesn't normally happen, we can use electricity, we can use the electrical energy of this battery to pull and push the electrons to make this reaction happen. Okay, so this is kind of a broad, big picture overview of electrochemistry. Now I want to show you two examples of these situations. One where we're using a chemical reaction to create electricity, and one where we're using electricity to make a chemical reaction happen. So here's how chemical reactions can create electricity. And to do this, to make electricity using chemical reactions, we often use a device called a galvanic or a voltaic cell. I've drawn one right here. The version that I've drawn uses zinc and copper metals. So let's take a look at the chemical reaction that's happening in this galvanic cell that is what's creating electricity. So here's a chemical reaction. We said that that galvanic cell used zinc and copper. So if you take a neutral zinc atom and put it near a copper 2+ ion, electrons naturally move from the zinc atom to the copper. And so what happens there is the zinc takes on a 2+ charge because it loses 2 electrons, and the copper becomes neutral because it gained 2 electrons. So why does this happen? Well, it happens because there's kind of a tug of war between these atoms. Cu2+ has a strong pull for electrons, and zinc, Zn, has a weaker pull for electrons, and that's why the electrons move. We can describe how they move in terms of oxidation and reduction. Zinc over here is losing electrons, so it is oxidized. Cu2+ is gaining electrons, so it's reduced. Now, the most important thing about this process is that it happens on its own. All you got to do is put neutral zinc near copper 2+, and the electrons just naturally move. It happens on its own. This is a process that we can call spontaneous. It's spontaneous. It just happens on its own. Now, a really common question, that's a great question, is people say, okay, yeah, but like, how do you actually know that the electrons are going to move from zinc to copper? How do you know that copper has a stronger pull for electrons? Well, you can look it up. There is this chart that we'll be using a lot in electrochemistry that's called the standard reduction potentials. And it lists elements and compounds in terms of how strongly they want to pull electrons. So the higher you go up here, the more these elements want to pull electrons towards them. So we got copper 2+ up here, and we got zinc down here. So the way this chart works is if copper is up here, if it's above zinc down here, then copper is going to be stealing electrons from zinc. Copper is going to have a stronger pull. So that's how we know that copper is normally going to be pulling electrons from zinc, and that this reaction is just going to happen on its own. So this reaction, as we said, is what's going on in a galvanic cell. So let's see how we can use this galvanic cell to create electricity from this reaction. Okay? Well, we said that zinc is going to be giving electrons to Cu2+. But when these atoms just give electrons to each other just like that, it doesn't really create electricity that's very useful for us. But if we can separate the zinc and the copper 2+, then we can make the electrons travel through a wire in order for them to move. And that is exactly what we do in this galvanic cell. Okay, check this out. We got zinc here in this container, and then we got a whole bunch of Cu2 plus in this container. There's also Zn2 plus here, but it's not really that important. So what happens is the electrons want to get from this zinc to this Cu2 plus, but in order to do that, they've got to go through this wire. So this is the path that the electrons take. They're moving through this wire to get from the Zn to the Cu2 plus, and check it out. They're moving along this wire, which means that they are creating electricity. They go into this piece of copper, and then they move here wanting to get to the Cu2 plus. So we got electrons moving in this direction, and as I showed earlier, we can even take a light bulb or something and put it between here, and the light bulb will light up because there's electricity moving through this wire as the electrons naturally, spontaneously move from the zinc to the copper. All right? Now, in electrochemistry, we often want to describe what is happening in a device like this using oxidation and reduction. We want to be able to talk about the different parts of a galvanic or voltaic cell and say what's happening to them with electrons. So here are just a couple words that we'll need to know. These two pieces of metal, the zinc and the copper, are called electrodes. The electrons are going into the electrode and coming out of the electrode. And now we can name these electrodes based on whether oxidation or reduction is happening there. Okay, here are two words that we use all the time in electrochemistry. The anode is where oxidation happens, and the cathode is where reduction happens. So let's look at what's going on here. Okay, we got zinc. What's going on with the zinc? Well, we know that zinc is losing electrons. It's being oxidized because the electrons are moving out of the zinc to get over here to the Cu2 plus. So the zinc is losing electrons, it's oxidized, which means that the piece of zinc here is the anode, the place where oxidation is happening. Over here, the copper is where electrons are getting added to the Cu2 plus. So the piece of copper as an electrode is the cathode. It's where reduction, it's where gain of electrons is happening. So the zinc is the anode because it's a site of oxidation. The piece of copper is the cathode because it's the site of reduction. So this is how a galvanic cell uses a spontaneous chemical reaction that happens on its own to create electricity. Okay, so anode, cathode, how are you going to remember them? Well, this is a really easy mnemonic, a way to remember it, okay? Chemical reactions happen that wouldn't happen otherwise. Using electricity to make chemical reactions happen is a process called electrolysis. We do electrolysis in a device called an electrolytic cell. I got a diagram of one of these here. And in our example, we're going to see how we can use electrolysis in an electrolytic cell to take water and split it apart into hydrogen gas and oxygen gas. So just like the reaction we saw earlier with zinc and copper, this is also an oxidation reduction reaction. We got electrons moving here. To understand how they move, we got to take a look at the oxidation numbers for the different elements here. Hydrogen's oxidation number is going down, which means that it is gaining electrons. It is reduced. Oxygen's oxidation number is going up, which means that it is losing electrons. It is getting oxidized. So we can kind of sum up what's going on here with a diagram like this. Electrons are moving from oxygen, which is losing them, to hydrogen, which is gaining them. But this is a problem, okay? It's a problem because it goes against what oxygen and hydrogen normally do with their electrons, okay? Oxygen has a stronger pull for electrons, and hydrogen has a weaker pull for electrons. So if it could, oxygen would want to take electrons from hydrogen, and hydrogen kind of would be willing to lose them. But for this reaction to happen, we're asking that the opposite take place, okay? Oxygen is usually stronger, but we're asking it to give up electrons. Hydrogen is usually weaker. It usually loses electrons, but here we're asking for hydrogen to gain electrons. And we can look again at this list of standard reduction potentials just to see who's stronger and who's weaker, all right? Oxygen is up here. The further up you are, the stronger pull you have for electrons. Hydrogen is all the way down here, so you can see that oxygen really wants to take electrons from hydrogen. But instead, we're asking oxygen to give electrons to hydrogen, okay? So based on that information, this is a reaction that doesn't happen on its own because oxygen doesn't want to give up these electrons. So we can say that it is not spontaneous. It's not going to happen on its own. We're going to have to use electricity to make it happen. And it turns out that a battery, the electrical energy from a battery, can pull the electrons from oxygen and push them to hydrogen. It can force this reaction to happen. Here's how. So we can make this process happen by using an electrolytic cell. This is some water here that we want to break down. We've got these electrodes, and the electrodes are connected to a battery. Okay, so normally oxygen has a stronger pull for electrons, but we can use the strength of the battery to pull electrons away from oxygen, okay? Here, hydrogen would normally give up electrons, but we can use the battery to push electrons to hydrogen. In terms of oxidation and reduction, this means that oxygen is losing electrons, so it is getting oxidized. Hydrogen is gaining electrons, so it is getting reduced. These electrons are getting pushed to it from the battery, okay? So what about anodes and cathodes? Remember, anox, red cat. Anode is where oxidation happens. So over here is the anode, the site of oxidation, where oxygen is losing electrons. And over here is the cathode, where hydrogen is getting reduced. So this is how electrolysis happens. We force the electrons to leave oxygen and we push them into hydrogen, making this process happen using a device like this called an electrolytic cell. So that's an introduction to electrochemistry. We looked at the two ways that chemical reactions and electricity interact. Certain chemical reactions, those that happen on their own, those that are spontaneous, can create electricity. In order for that to happen, we separate the two things that electrons are moving between, and we put a wire in between them so the electrons will move through the wire. Electricity can make certain chemical reactions happen that wouldn't happen otherwise if a certain atom doesn't want to give up electrons or another atom doesn't want to gain them. We can use the electrical energy from a battery to pull electrons and to push them, forcing oxidation-reduction reactions like this to happen. We looked at how galvanic or voltaic cells use processes like these. In this video, we're going to talk about galvanic cells, which are also called voltaic cells. So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation-reduction reaction. But we'll talk more about that later. Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation-reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right? So I now want to talk about the parts of a basic voltaic cell, one that you could actually make in the lab. So here's what they are. First, we start with two beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with that. So we got these two solutions. Then we take a piece of zinc metal, like this one right here, and put that in the zinc sulfate solution. And then over here, we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal wire, and we use that to connect the two pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They
border, I think, is important, because this is where I'm going to try to get a little more contrast. And if you come down to these nightmare ones, okay, do you see how those are getting more contrast? And I actually like the nightmare one, which will give my active window sort of bright white over sort of a deep plum. And I think that is both attractive and very readable. Okay, I think that is attractive and very readable. So we are going to go with that. You see, you could install a new theme here. You can download them and you can install them. But like I say, we're just going to go with the themes that we have here. And now we are going to go to font, and on the font, nothing really here, and then other, nothing really anything here that we need to do either, I think. And so we can close at this point, and that is looking kind of strange. Let me go back. Something funny happened somewhere along the way. Preferences. Let's go to, where was that? Appearance and settings. Okay. Fit image onto screen. I think that was wrong. What I want to do is center it on the screen like that. There it is. Okay. So that was appearance and settings. And now I think I have a nice clean desktop that I really like. Now let me see. Okay, one more thing that we want to do. I hate 2-click machines, right? Why overwork yourself with 2 clicks where you can do it with 1 click? So we're going to come down here to the little icon of the file cabinet. That's your file manager, and you pop up sort of a, what would be a very familiar view of a folder view of your system. And then we're going to come up to edit, and we're going to go to preferences, and up here at the top, open files with a single click, and then I am going to say close. And then that makes me very happy. Okay, that makes me very happy. I've got a clean desktop. I've got a readable font, and the font sizes are large enough that I can read them and you guys can read them. Okay, now let me try to kind of help you with one last thing in this lesson, and that is something that I found that was probably the most confusing thing to get figured out, was this screen, this little panel bar down here. And again, it calls it the menu bar in one place, and then in other places it calls it the panel. And if you get this thing goofed up, it's very hard to get it right. So I want to kind of take you through it and explain it, and explain where you can understand the terminology. Usually this whole thing all the way across, and I need to go to a different view here. I think I need to go to a different view where you can see the whole desktop. So say goodbye to the live shot of the Raspberry Pi, and then we're going to go to this shot, and then I need to edit this very briefly. I'm sorry I didn't have my windows already, but I need to make sure that you can see the whole desktop. Okay, I think that. And I need to go to a different view here. I think I need to go to a different view where you can see the whole desktop. So say goodbye to the live shot of the Raspberry Pi, and then we're going to go to this shot, and then I need to edit this very briefly. I'm sorry I didn't have my windows already, but I need to make sure that you can see the whole desktop. Okay, I think that will work. Okay, there. Now you can see the whole desktop, and I will probably have to get further out of your way before this is over. But okay, this whole area down here is the panel. If I right mouse click on it, you can see that it talks about the taskbar, it talks about the panel, and it talks about panel settings. So there's panels and taskbars, and there's also applets, and there's also the menu. So the whole thing is the panel. From the left to the right down there, that is the panel. Now this little icon here, this is the menu. And when you click on it, you get all of your menu items. Okay, all of your menu items. And if we wanted to edit that, we would go to Preferences, and then we would edit the menu. Okay, and then you can see here are what we have. This is what we have. This is what's available to us. Like if we turned off universal access, then over here you can see that universal access is grayed out. It's not going to be on the menu. Let's just look at that. We'll come over here, and sure enough, universal access has disappeared. So that is how that works. But again, like I showed you earlier, the other part of this that you need to understand is if we come into Preferences and we go into Menu, you also can change or edit the sub-menus that are in the folder. So to do that, I would come over here, and like Preferences is a group of items, and then everything in Preferences shows up here, and then I can turn those on or I can turn those off. And so that is kind of what you need to know. This is the panel, this is the menu. Well, then what is this? This is the launcher. Okay, and so what I'm going to do is I'm going to actually come in and kind of show you. I think I need to edit this just a little bit more to make sure that it is absolutely readable for you. Okay, and I'll kind of move it over here. Okay, and now I will bring you to that view. Okay, I think you'll be able to see it now. Okay, so what we're going to do is we're going to play around with the panel. Now, what's the taskbar? Okay, so taskbar settings. What is the taskbar? Okay, this sort of controls what the taskbar looks like, and the taskbar is this area here that is going to show the things that are actually running. Since we don't have anything running, nothing shows here, but let's say that I clicked on the file cabinet, and then you can see in the taskbar we have this icon show up. Now what's confusing to me, and we'll fix this in a minute, if this is the launcher is kind of right up against the taskbar, so when you look at it, it's hard to say what's part of the taskbar and what is part of the launcher. So I don't like that very much. But what we're going to do is we're going to come in and we are going to right mouse click on the panel, and we are going to say panel settings. Okay, panel settings. And the first thing is the geometry. Okay, you can have it on the bottom, you can have it on the top, you can have it on the left or the right. Well, it started out on the top and we moved it to the bottom, and so we are going to leave it there. Now let me show you one of the goofy things that I don't know if they'll fix this at some point. Let's move it back to the top and then say close. What happened when it moved it to the top? It changed the icon. Why did it do that? That's annoying. So let's come back and say panel settings again, and let's move it back to the bottom, and look at that. It is still that one. And so what I'm going to do is I am going to come into menu settings. Okay, so let me do that very carefully. I right mouse click on the icon, menu settings, and where it says start here, I go back to RPI. Maybe you like that little squiggling thing, but I like the little happy raspberry. Isn't that goofy? Maybe by the time you take this class, maybe the version that you download, they would have fixed this little glitch. But that is that. Now let's come over, let's go back to panel settings, okay? And so this is all more or less right. You know, you could adjust things if you want. If you want to make it a little bit bigger, a little bit smaller, you could make the height bigger and the icon smaller, whatever you want. You could kind of adjust that if you wanted to. But now let's come to appearance. I like to use the system theme. If I want to change this, I want to change it in the theme, not in the individual element. Now, this is where your real action happens, and that is your panel applets. And this is very, very confusing. But if you look at it, this shows what you have as you come across. What is the first thing you have is the menu. That is the menu there. Okay, that is the menu. What is the next thing? It is a spacer. Okay, it is a spacer. So this little globe, which is your web browser, and this are not absolutely against each other. There's a very small spacer between them. Now, what is this stretch business? Well, if I turn on stretch, it moves it out away and sort of makes it stretched out between the, and I'm really going to have to get out of your way here so that you can see this, and then I'll come back in a minute. Little munchkin me. Okay, so what that does is that stretches. I make that spacer where it stretches, and it puts a stretch between this group of icons and this group of icons. Okay, and so that sort of stretches it out. But we'll turn that off. What did I do? We'll turn off the stretch on the spacer. Now, what is the next thing? The next thing is the application launch bar. And these things are things that you have an icon that allow you with one click to open a program. So you don't have to go to the menu. You can just open them with one click. So what do we have for one click? Well, the browser, the file system, and the terminal. Now, what I don't like is, you see, like my panel preferences, my panel preferences is not part of the application launch bar. It is part of the taskbar. It is part of the taskbar. Okay, and so it's very easy to get confused about what is the application launch bar and what is the taskbar. So what I like to do is I like to put a stretch on this spacer here, and then that taskbar is over away from the launch bar. And so now if I start a few things up, what you can see is it's very clear. These are the ones that are open, and these are my choice of things that I could open. Okay, let's say there's some things I really want here that I want just easy access and quick click to access them. And so here on my application launch bar, right, my application launch bar, I want to add. And what do I want to add? Let's look here and see if there is anything that is really good. I'm trying to see if there's something. Okay, I don't see anything that I really have to have. I was hoping there would be something cool there that wasn't there, but I don't really see anything. Let's look at preferences on that launch bar and see if we're given any more things. Maybe we are given more things here. So instead of adding is just adding kind of system things. If we click on application launch bar and we go to preferences, then I cannot stand being that munchkin. There, that's not quite as embarrassing. Okay, so what we have done is we've gone to panel preferences, we've clicked on application launch bar, and now under preferences, what I can add is I can add a program. So if I look at programming, I could. Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 2 in our incredible new tutorial series where you're learning how to use the Raspberry Pi. What I'm going to need you to do is pour yourself a nice tall glass of iced coffee. That would be straight up black coffee poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is sponsoring this series of lessons on the Raspberry Pi, and in these lessons, we will be using the most excellent Sunfounder Ultimate Raspberry Pi Kit. Now, we will be starting with if you come from a Windows world, or if you come from a Mac world, you sort of have folders inside of folders inside of folders, and you were probably very comfortable navigating with this folder view. And we can kind of see the file system here. You start up here at the top folder, the root folder, the slash folder, that's called the root folder. And then you can see inside of the root folder, there was this folder called home. And then if you go inside of home, there is your user folder, Pi. That is your Pi, because that's the default user. When you install the Raspberry Pi operating system, the default user is Pi. And then inside of Pi, you have things like your desktop, your documents, your downloads, your music, and everything. If you added another user, he would also be inside of home, and he would have a different name, and he would have a different folder here. Okay, you should be very familiar with that. But how do we do that same type of thing, but instead of using excuse me, a graphical user interface, we were using the terminal, the Linux terminal, the command line. Well, to get there, you need to come down to the lower left, and you see this little icon that looks like a computer screen or a terminal. You click on that, and then your terminal will pop up here. And then what you see is you have a command line waiting for you to enter a command. But before we enter a command, let me just kind of make you feel comfortable with what you are looking at here. The first thing it says is Pi. Well, what is that? Pi is the username. Since you are the default user, when you boot up Raspberry Pi, you are user Pi. And then it says Pi at Raspberry Pi. Raspberry Pi is the machine name. It's the name of your particular Raspberry Pi. And again, that's the default that it comes in when you boot. Now, if you wanted to change your machine name, you could come down here to the happy little menu, the happy little Raspberry Pi icon that brings you to your menus. You could come to Preferences, and you could come to Raspberry Pi Configuration, and then that pops up with this little menu box here. And you can come over to System, and if you look at host name, you can see that your host name is Raspberry Pi. Now, if you change that, then it's going to change up here. Now, I would demonstrate that, but that requires a system reboot. And so I don't want to slow us down with a system reboot, but just know that if you change the name of your machine, okay, and then reboot your machine, then your machine name will show up here. So you've got your user at your machine name, and then you have a colon, and then you've got this $sign. That $sign means that it is waiting your command. Now, what you see this little icon that looks like a computer screen or a terminal. You click on that, and then your terminal will pop up here. And then what you see is you have a command line waiting for you to enter a command. But before we enter a command, let me just kind of make you feel comfortable with what you are looking at here. The first thing it says is Pi. Well, what is that? Pi is the username. Since you are the default user, when you boot up Raspberry Pi, you are user Pi. And then it says Pi at Raspberry Pi. Raspberry Pi is the machine name. It's the name of your particular Raspberry Pi. And again, that's the default that it comes in when you boot. Now, if you wanted to change your machine name, you could come down here to the happy little menu, the happy little Raspberry Pi icon that brings you to your menus. You could come to Preferences, and you could come to Raspberry Pi Configuration, and then that pops up with this little menu box here. And you can come over to System, and if you look at host name, you can see that your host name is Raspberry Pi. Now, if you change that, then it's going to change up here. Now, I would demonstrate that, but that requires a system reboot. And so I don't want to slow us down with a system reboot, but just know that if you change the name of your machine, okay, and then reboot your machine, then your machine name will show up here. So you've got your user at your machine name, and then you have a colon, and then you've got this $sign. That $sign means that it is awaiting your command. It is awaiting your orders. But between the machine name and the colon and the command prompt wanting a command from you, you see that we have this little squiggly. That squiggly is the shortcut to indicate that we are in your or my home directory. So the squiggly is the shortcut for the home directory. Well, what directory are we actually in? I don't want to know the shortcut. I want to know the actual path name, and we can figure that out by typing in pwd, which is print working directory. So if I put in pwd for print working directory, it shows me that I am in the folder /home/pi. Well, let's come back over to our folder view, and you can see that if we go up to the / the root, we can see inside of root, one of the folders is home, and then inside of home is the users, and we have one user pi, and then we are in the pi folder. So we are in the / for root, that's /home/pi. And then we will come here, okay? And so that is what is telling us we are in the /home/pi. So you've learned your first Unix command, pwd for print working directory, and it shows you specifically what working directory, what directory you are in. Okay, now let's learn our second Linux command, and that is we can go to a different directory. So let's go to our root directory. The root directory, root means the very, very top, the ultimate top level folder or the top level directory. And so we could go there by putting cd for change directory and then a /. So that's change the directory to the root. Okay, now what is in the root? One way we could see what is in the root is come in and look here and go to the root, and you can see there's all of these folders. But again, we don't want to be messing with that graphical user interface. It just slows us down. So we can do an ls, and it shows us the folders that are in our root directory or our top level directory. It shows us the folders that are in there, and this matches what you would see if you went back and looked at your graphical user interface. Okay, so there we are. Well, now how do we get back to our home directory? Well, I could go cd, and then I would go home because I see the folder home here, and so I could say cd for change directory home, and then you can see I'm in the /home, and now I could do an ls again to list what's inside of that, and the only thing in there, as you already know, is pi. So I can go to the pi folder by saying cd pi like that, and now if I do a print working directory again, I'm in the /home/pi. Well, let's go back, and I could go to change directory to the root, and let's say that I wanted to just go to pi, and I just said cd pi. Well, I get an error because you've got to give it a very explicit path. If I'm in root and I say go to pi, it doesn't see pi because it doesn't drill down into the folders. It only sees the folders immediately inside of itself. So what is inside of root? These folders. I think I perhaps should get a little bit further out of your way. Okay, I think that'll make you a little happier. You can see that these are what are inside of root. And so now I would do cd home. Okay, and then I could do and then I'll do an ls. Now you can see pi, and so now I can do a cd pi like that. Okay, now what if I did cd back to root, and now I did the ls, and now I said change directory home. That's all good. Now what if I said change directory /pi? Okay, let's do an ls so that you see pi is there. Okay, now what if I did a cd for change directory into /pi? Well, I get an error, no such file or directory. Why? when you put the leading slash, when you put that leading slash that you see here, that says go back to root. So when I did cd/pi, it went cd, it went all the way back to root, and then it didn't see pi there. And so the right way to do it would be, let's look, ls, there's pi. I just do cd to pi, and then it's happy, and now boom, I am back in my home directory. Now you can also string these things together, so you can do them all at once. So I'm going to go cd, and where do I want to go? I want to go all the way to root, and then I want to go to home, and then I want to go to pi, and then I want to go to I erased all that. So I want to go cd, I want to go to the root, I want to go home, I want to go pi, and then I want to go to videos, okay, because you can see right there there's a videos folder, and then I go boom, and now I am in the videos folder. All right, now I'm in the videos folder, and if I do an ls, you can see that there is nothing in there. Well, what if I wanted to go to music from videos? So I'm in videos and I want to go to music. Well, one way I could do it, I could go cd, I could go all the way back to root, and I could say go home, go pi, and then go, what did I say? Did I say music? Okay, let's go music. It's happy, and there's no music there. All right, now let's say I want to go back to videos. Instead of going all the way back to root, what I could do is I could go up one, and I go up one by going ... That takes me up one back to the pi folder, and then slash, and then I can come back into videos like that, and boom, I'm in videos, and there is still nothing there. Also, let's just say that I go to home, I go to root, and now you can see I'm back at the root with all these system files in there. What is an easy way that I can go back to my home directory? I could go /home/pi, or an easier way, I could say cd squiggly, and then the cd squiggly will take me back to my home directory. Really, I don't use the squiggly as a shortcut, because when I'm just navigating my own little area here in the terminal, it works great. But if you start programming and you start using the squiggly inside of programs, inside of path names, that can generate all types of confusion, and it can generate all types of problems. And so what you really don't want to do is, I just don't use that as a shortcut, because it can, if I get in the habit of doing it, then I'll do it in a program, and that can sometimes cause problems. Okay, so where are we right now? Where are we, PWD? We are in our home/pi directory. And then if we look there, we have all these things. These things are all pretty much empty. Well, let's move on now. You kind of find out about how to find your way around. ... goes up one. I can't help it. Let me do one more. What if I did cd and I went ... What would that do? That would take me all the way to root, because the first ... is going to take me to home, and then the second ... is going to take me all the way to root. And you can see the slash there. I am in root. If I do a ls for list the contents of the directory, you can see there we are. So I will now go cd, I will go back home, and I will go back to pi, and now ls, there I am in my home directory, the /home/pi. Okay, does that make sense? All right, we have played around and we have made our way around. Okay, what if we wanted to install some software? Most software you install using the command apt-get, apt-get, and then the program name. So let's say I want to install PuTTY. PuTTY is a little application that allows you to SSH or remotely log into other computers. And so I'm going to say apt-get and then install PuTTY, the program PuTTY. This pro tip, this only works if you're on the internet, because it's going out to the internet to look for the program to install. So I'm going to say apt-get install PuTTY, and then, ooh, that was very bad. I missed I hit the slash key instead of hitting the enter key. And this will show me, though, that if you want to go back to a previous command, hit your up arrow. And if I hit my up arrow, I get my last command back. and then I'm going to backspace over that slash that shouldn't have been there, and then enter. And then it says, could not open lock file, permission denied. Anytime you see something with permission, it means you, the user Pi, just on your own, you don't have the permissions you need to do the command. And so you can't just install something using a command like apt-get. What you have to do is you have to go into super user mode, and you use a super user do, which is sudo, which is SU for super user.
Hey everybody, let's talk about arrays. An array is a data structure that can store many values of the same data type. Here's an example. Let's say I have a variable named price, and I have the price of maybe one item in a fictional store of ours. So by using an array, we can actually store more than one value, but it has to be of the same data type. So I can turn this variable price into an array, and I can do that by following the name of the variable and add a set of straight brackets. And then any values I would like to add to this array, I will surround with a set of curly braces. And there we go, we have turned our variable price into an array. But I'm going to change the name to prices because I think it would be more descriptive, because we can store more than one value now. So we can add multiple values, each separated with a comma. So let's say we have another price that is $10, $15, $25, and maybe $20. Now you may have noticed some parallels when we create a string. It's really an array of characters. So if I need a name, we would say the data type is char, and we will create a name array followed by a set of square brackets, and I will set this equal to some amount of characters. A string is really just an array of individual characters, and with my name here, I have 3 individual elements, 3 individual values. Now, if I need to access one of these values, I need to use an index number. So let's print one of these numbers. So printf, I'm going to use the format specifier for a double, and I'm going to list my array name, prices, then follow this with a set of straight brackets. Then I need an index number. So each spot within an array is known as an element. So we have 5 elements within our array. And to access one of these elements, I need to list an index number. The first element has an index